Let's take a look at the details of how Eratosthenes calculated the circumference of the Earth using just a few measurements like the length of a shadow. So he had heard that in Syene down here, on the summer solstice at solar noon, there were no shadows cast. You could look down a well, you could see the reflection of the sun, so there were no shadows that were obscuring the sun there. In Alexandria, he performed the same experiment. On the summer solstice at solar noon, he looked to see if there were shadows, and there were. So on the same day, at the same time, in two cities that are far apart, but not extremely far apart, Syene saw no shadows, Alexandria saw shadows. And using just that information, we can calculate the circumference of the Earth. Let's look and see how. So this is a screenshot of Google Earth, where Alexandria is today and where Syene was back then. And you can see this is a curved shape. We know that because we do now know for certain that the Earth is a sphere, or very close to a sphere. And so you can think of slicing the Earth in half along one of these longitude lines. These longitude lines run from the North Pole to the South Pole, and we could just cut straight down one of them, and it would give us basically a circle. The face of that would be a circle. And Alexandria and Syene are a little bit off longitudinally, but they would almost exactly be on that same circle, right on the surface of it. And this is what it would look like as a cross-section. It would look something like this. Now this is a diagram of the sun rays coming in and the shadows that either are cast in Alexandria, right here, shadows not cast in Syene. And Eratosthenes' really brilliant idea was this. We have these sort of radii coming out from the center of the Earth, assuming the Earth is a sphere. And they connect to the cities at different points on the radius, or on the circumference. And Eratosthenes had this idea that if we could figure out what this angle measure is, that it would be a certain proportion of this entire circle. And his thought was, if we knew what that proportion was, if we know what this angle measure is, and we know the distance between these two cities, which they did because, well, they had lots of different reasons to. They had surveyors, they needed to know who owned the land. The Greeks were also well known just for hiring people to pace out distances, so they're very into measuring distances. They knew the distance from Alexandria to Syene. So if they had the proportion of the circle, and they knew this distance, he could hypothesize that this distance was that same proportion of the entire circumference, and we could figure out the circumference of the Earth. So the tricky part here, the thing we need to know though, is what is the measure of this angle? And how could we possibly maybe use shadow lengths and angles to figure out this angle? Well, it turns out we can use geometry to do that. Let's take a closer look at this. So if we zoom in, we can see the sun's rays are all coming in parallel. The sun is far enough away that the sun's rays arrive at Earth essentially parallel. And when they get to Syene on the summer solstice at solar noon, they are parallel to this line of Syene going to the center of the Earth, this radius. And that is why they don't cast any shadows, because they aren't intersecting objects obliquely. Perpendicular objects, at least, which wells tend to be perpendicular to the surface. In Alexandria, however, the angle is slightly different. This is, again, the angle going to the center of the Earth. And these rays now intersect objects and cast a shadow. So we'd see a shadow right here. And it looks something like this if we were to look at it from the ground. So in Syene, the rays are coming straight down. In Alexandria, they're kind of going slanted. Well, it turns out since this is perpendicular and this is the ground, this is essentially a right triangle. And we really like right triangles in geometry, right? Because we have lots of rules we can use on them. Lots of different ways we can figure angles and side lengths out. Additionally, we know the height of this obelisk, or we know the height, we can generally measure the height of whatever it is we are taking the shadow of. They built obelisks at particular heights, so we knew what the height of it is. I just chose 15 feet here. Feet is a modern measurement. That is not the measurement they would have used in ancient Greece, but we can think of it as 15 feet. It could be an equivalent measurement. And then we could also measure the shadow. So if we have this measurement and this measurement, we can then get all the other angles as well. Now there are a few different ways to do this. There are trigonometry functions, which we won't go over in Math 1. But just the simplest way to do this would be to pull out a protractor and measure this. Measure this angle right here. You don't have to pull out the protractor in real life and climb up the obelisk and do it up there. You can model this. You can just draw this triangle proportionate. Make sure you do 15 units on your graph, 15 units up and 1.9 units across, and then you can actually measure this angle, and it will just be a scaled down version of the triangle in real life. Okay, so Eratosthenes did this and said, this angle right here is 7.2 degrees. Now, how does this get us to ultimately that question that we were asking though, which was, how do we find the central angle? That's what we call this when you look at the angle between two radii. How do we find the central angle using this angle at the top of the triangle? How can we use that? Well, let's zoom out again. Here's our picture of Alexandria and Syene, and we know this angle right here is 7.2 degrees. Well, there is a theorem we can use called alternate interior angles. And it says, when parallel lines are intersected by a transversal is just a line that intersects two other lines, the alternate interior angles are congruent. So interior angles are created, that means angles that are between these two parallel lines. And what we mean by alternate is they're on opposite sides of the transversal. So here we have alpha angle and beta angle, and we would say that those two angles are congruent, which is another way of saying that they measure the same degree. You may notice here we also have alternate interior angles. Those would measure different from these two probably, but they would measure the same as each other. So I'm not going to prove that here, we're just going to take this as given. You can look up a proof for that on your own if you would like to. But we do know that alternate interior angles are congruent. And you may have connected the dots that we have some parallel lines going on with these sun's rays. So here we are. We have this line here. If we were to extend the sun's rays, the line of the sun's ray, that would be parallel to this one down here, which also happens to be the radius of Syene. So now if we look at the angle we calculated, which is right here, 7.2 degrees, and we consider this blue line to be the transversal, then now we can say this line, remember we said this purple line is the parallel one, we can say this angle right here, this is the alternate interior angle. You can see it's on the opposite side of this blue transversal line, and it's between the two parallel lines. We can say that angle is also congruent. And that's how Eratosthenes figured out the central angle between Alexandria and Syene, just by measuring the height of the object and its shadow, and then figuring out what the angle was for that right triangle. So from that point, all we need to do is set up this ratio. We said 7.2 degrees over 360, that's the ratio of the central angle to the full circle, will be the same as the distance between Alexandria and Syene as a ratio to the circumference of the Earth. That's the original proposition we made. And we actually know this one. We know the distance between Alexandria and Syene. Like I said, it was common knowledge. In today's units, we'd say is about 790 kilometers is what they knew it to be, about 790. So all we do is plug that in and solve. 7.2 over 360 equals 790 over x. Now as my first step, I'm actually just going to simplify this fraction over here. 7.2 divides evenly into 360. If you look in your calculator, if you do 7.2 divided by 360, you get 0.002. Or if you do it the other way around, 360 divided by 7.2 is 50. So if we divide both the top and the bottom by 7.2, we get 1 over 50. And then this becomes much easier to solve. We can multiply both sides by x. We get x over 50 equals 790 kilometers. And we'll multiply both sides by 50. And we get 39,500 kilometers. That is what Eratosthenes estimated the circumference of the Earth was. Turns out that is only about 500 kilometers short of the actual circumference. It is a very, very close estimate and was achieved incredibly early considering the technology that was available.